The final thing we want to talk about in terms of eliminations is to look at cyclohexanes. Cyclohexanes, and this is specifically for E2 conditions. The cyclohexanes, as a consequence of the way the molecule is structured, we're talking about its shape, have some other special characteristics we have to talk about. So if we started with a molecule as simple as this, bromocyclohexane, and we added base to it, we would get exactly what we expect, the cycloalkene. But what happens if we put a substituent next to it, say a methyl group? Is that methyl group going to have an impact? So there's two ways that we could put that methyl group. Turns out the answer is yes. So recall that we've said that in general eliminations like to give us the more substituted alkene. And in the first molecule, that's exactly what we get. We get the more substituted alkene. But in the second case, we get something unexpected. We get the less substituted alkene. Why is that? Well, when it comes to cyclohexane, what is it that we should always look at? We should always look at it in its chair conformation. Now in this case, I'm going to put the bromine in the axial position and the methyl in the equatorial position. As we can see in our structure on the left, both of them are pointing up, and so I want my chair conformation to be the same way. Now why did I pick to put bromine in the axial position? Two reasons. First of all, bromine is generally smaller than methyl, so the methyl is going to want to be equatorial. But second, and more important here, remember that we said in an E2 that it requires the leaving group and the hydrogen to be 180 degrees apart. Well, if I use the other chair conformation here, what bonds are 180 degrees from this bromine? Well, it's these two carbon-carbon bonds. So there's no hydrogen that's 180 degrees apart. So in order for an elimination to take place in a cyclohexane ring, the leaving group has to be axial. Well, if that bromine is axial, this hydrogen down here is axial, and these two groups are 180 degrees apart, and we can get the elimination to take place. But what happens when we made these two groups trans to each other? Well, the most stable chair conformation is going to look like this with both of them equatorial. Now that's not a problem. With these groups being small, they can adopt the other conformation. It's significantly less likely, but it does happen. And then when it adopts this conformation, it can eliminate, and then the equilibrium can push the reaction forward. But in this case, where's the adjacent hydrogen? Well, the one on the more substituted carbon is equatorial. And it can't be axial if the bromine is axial. So because of this requirement, we can't get the more substituted carbon to perform the elimination. Now if we go to the less substituted carbon, we do have a hydrogen that's axial pointing down, meaning that it's 180 degrees apart from the leaving group, and it can eliminate. So in this specific type of case, we end up with the less substituted alkene, and again that's specifically because in order for an elimination to take place in a cyclohexane ring, the leaving group has to be axial, and the adjacent hydrogen that's being removed also has to be axial. If they're not both axial, they can't be 180 degrees apart, and the elimination can't take place.